This is the lab for the Gauss thin lens equation, and of course you have it posted in Blackboard. We need, so besides the theory that I just scrolled through, you need this table here to look at when you need a positive, when you need to use a negative, and so on. This is actually the setup that I will be using. Here are my example data linking the thin lens equations, so 1 over dO plus 1 over dI equals 1 over f. So these are my measurements. You don't have to replicate these are just always my example. And then I computed that the focal length 1 over f is this one here with a nice average of 10.0, which is exactly what that particular convex lens was supposed to be. And that's a positive number. All right, these preliminary observations and measurements, if it shows, it should be page 728. These you would have to do with the equipment that I supply to you. And you have to, besides all these other instructions here, the most important one perhaps is the standing up. The reason is the thin lens equation itself. You're looking with the lens at something on the table, and I prefer that you use something in print. Just open a book and just put the lens on there. And now, as you lift it up, you have a certain object distance, which is the print in the book, to the lens. And then you have a certain image distance, which is from the lens to your retina. Now, what's in the way is actually your eye itself. It itself is an optical instrument, has a convex lens in it, and so there's a second one there, which in this case we're not accounting for. So you would have to stand far enough away to make the image distance large enough that you will be able to see that, for example, for the convex lens, that when you're at the focal length, that it actually becomes blurry, because at that point when the image distance is large enough, then 1 over dI is virtually 0, and then you have 1 over dO equals 1 over f, and again that only works if you're actually standing up. The lenses that I supply are going to be 5.0 centimeter, and for the convex lens, for the concave lens it's going to be negative 20 centimeters. I'm not writing this down here because in this little experiment you're not going to be able to figure this out. This one you will figure out. There will be a blurry point, but again, only if you're standing up. For the concave mirror, on the other hand, notice that the convex lens and the concave mirror, they're kind of similar. Convex lens, concave mirror, as far as the data are concerned. So here, actually, I don't know top of my head what I'm going to give you there. And there should be the word blurry here as well, at just the right distance for the concave mirror. All right, so these are observations you have to do on your own. These preliminary observations, I will try to do them on the optical bench. We'll see. Scrolling down a little bit. This one here, we will definitely skip, because there's just no good way I could do that across the room and film myself. You could do it at home, but you would actually need a pretty dark room and a pretty bright light that has something on it that can be projected, like a really transparent light bulb where you can actually see inside the filament, and that can be projected. A faint candle might do it, but it would have to be a pretty dark room. So in any case, if you want to try it, give it a try, but overall we can skip this one. This is the setup, and this is at the heart of it. So this is what I will be doing. The convex lens here, then the concave lens, and apparently that table is pretty short. Then the combination convex-concave lens, then concave mirror, then convex mirror. And so again, that will be at the heart of it. This one here, table 7, the lens-maker equation, I will likely skip as well. And then what I like you to do is just write down the data and hand those in to me, and you may skip the conclusion for this one. So here are the preliminary observations. And I'm going to start with the convex lens. I put it closer than one focal length here, so at 5 centimeters it's about at 4 centimeters, and I cannot project anything. Really what you see here is actually the outline of the lens itself, but I cannot see the flame as an image. It's pretty close. I wonder if it's going to catch on fire here or melt or something. But the only thing I really can do is I can look through it, and it works as a magnifying glass. But that's not what this table is about, which is about getting images here on the screen. So I'm going to put it past the focal length just a little bit, and here we can definitely see there's the flame, and it is a real image because it projects. Here is maybe the best focus somewhere. It's definitely bigger, and it's upside down too. Then I put it at twice the focal length, so 10 centimeters away, because the focal length is 5 centimeters. And let's see, it should be actually right here. The image distance also being 10 centimeters. And again, it's real, inverted. That's what I meant earlier, inverted. And it's the same size, actually. Then I get it past the focal length. I'm sorry, twice the focal length, somewhere over here, and I have to get really close to actually get it here. Still real, still inverted, and it is definitely smaller. Then I'm going to do this for the concave lens. And here the trick is, no matter where I try it, I don't get an image. And of course the reason is the light rays are diverging, so I can't get a real image on here. I do get a virtual image, so I can look at it and it actually makes it smaller. That's because I myself have a convex lens in my eye which projects it onto the retina, and so I make that virtual image to become real image on my retina. The convex side of the mirror of a mirror behaves in the same way no matter where I try it, just like the concave lens, the convex mirror behaves in the same way. I never can get an image. So here is the concave mirror, and when I hold it, I know that its focal length is 10 centimeters, so when I hold it closer to the flame, I cannot get any image, just like the convex lens, the concave mirror behaves in the same way. It is larger when I look into it, because I get the virtual image here where, again, with the lens in my eye, the convex lens in my eye, I can actually see it. So within the focal length, up to the focal length, nothing is happening there. In fact, at the focal length, it all gets kind of blurry, except, of course, my convex lens is screwing that up. And then when I go beyond it, now I get an image, and just like the convex lens, it is a real image, it is inverted, and it is larger. When I get to twice the focal length, still real image. Well, actually, let me find it first. Where did it go? Should be the same distance here. Oh, no, it should be here, actually. Where is it? Where is it? I just had the image, right? So there's my more or less nice image there. And when I go further away, I have to get closer or further. I should get closer. There we go, there we go. There we go. Okay, where... Okay, here I got a nice image. I'm trying to find that. There. Okay, alright. Okay. So I really actually have to go here and see if my paper catches on fire on my screen. Alright, I finally got it, which makes sense, because the image distance ought to be the same as the object distance. So it's still inverted, real, and now it's the same size as twice the focal length. When I go further away from that, it's still going to be Let's see if I can catch it again. There it is. It's smaller, and it's real, and it's still inverted. So the candle is at 1 centimeter instead of 0, so I just have to subtract the 1 centimeter. The lens is at 8 centimeters, so I have an object distance of 7. And then I move the screen, and of course I'm using the convex lens with, there we go, that looks like the best. I'm gonna get a difference of 17.5 centimeters. Okay, then I'm gonna put this one at a distance of 9 centimeters. And I'm getting, let's see, ooh, getting really good. Yeah, about here. I want to say 11 centimeters for the image distance. Then I'm going to move this one to a total of 11 centimeters. And this one here I'm going to measure, let's see, yeah, about here. So that's 8.6 centimeters. Let's see, I actually have to write these down. So I have to check if I'm actually still recording. So then I'm going to go to 13 centimeters. And let's see where we get that. And yeah, about here, 8 point, how much is that? 8.5 centimeters. Then I'm going to go to an object distance of 15. Okay, that looks pretty good. So I'm reading 7.5 centimeters. Then I'm going to go to an object distance of 17. And of course I always measure object and image distance from the lens. So at 17 centimeters, let's see. Oh, that's tricky. Oh, there we go, there we go. I want to say 6.5 centimeters. And then finally, at an object distance of 19 centimeters, I want to say that looks pretty good. I get 7.0 centimeters. Okay, now I'm going to use the concave lens. And no matter what I try, I usually let students do that, fiddle around with it for a while until they figure out it doesn't project. And of course it cannot project because it would give us a virtual image. The optical rays are not converging, hence we cannot get a real image. Of course, if I look at the candle, I do see something. I see a virtual image, which is always smaller, which is what you're supposed to figure out with the lenses that you're supplied with. But in any case, it doesn't project. So this is the convex side of the mirror, and it does the exact same thing as the concave lens. It doesn't project, because instead of converging, you would have diverging rays, and yeah, you do not get a real image. What I can do is I can look into the mirror and I see the virtual image simply because the convex lens in my eye, of course, projects that virtual image onto my retina. So now I put the convex and concave lens together here, right here, starting at a distance of 12 centimeters. And I'm going to try to get an image, and here it was. Let's see, about, that looks pretty good. At a distance of, let's see, 16. And I'm going to put the object distance at 14. And I'm going to get an image at 13 centimeters. Put the object distance at 16. And I get an image distance of, let's see, yeah, about there, 12 centimeters. Object distance of 18. Alright, so that's 11.5. Object distance of 20 centimeters. So yep, that looks pretty good. Let's see, that one is 10.5. Object distance of 22 centimeters. Yep. So that is pretty much 10 centimeters. Object distance of 24 centimeters finally. And let's see. Yeah, that looks pretty good. So here I want to say also 10 centimeters, maybe a little bit less, 9.8 centimeters. Did I already say that it took me quite a while to find a spot in this room where the candle is actually behaving nicely? So in any case, I put the candle here at the 30 centimeter mark. I put the mirror over here, and it's the concave side of the mirror that is pointing towards the candle, and I put the screen over here, and I'm trying to get a good image here. Let's see. So I want to say, let's see, that's not true. Oh, here we go, here it is. So I'm 16 centimeters away, and I get, that's the object distance, and the image distance is 26 centimeters. Yep, that's about the best image. By the way, when I took these measurements just before, I had perfect measurements. Let's see if I can replicate that. So in any case, let's see. Yep, that looks pretty good. I'm now at, yeah, here we go. I'm now at 15 centimeters object distance, and it's 30 centimeters for the image distance. The mirror doesn't give that great of an image, but we can see definitely a difference here. Blurry, and then in between we got it somewhere here. So now I'm in an object distance of 14 centimeters, and here we go, image distance of 34. Okay, object distance of 13 centimeters, and let's see, yep, about here, yeah, 43 centimeters. And then here, object distance of 12 centimeters, and apparently it's way over here. Yeah, it doesn't get better, so it's probably, yeah, it's probably this one here. So that one is 50 centimeters image distance.